Okay, so we're going to get started the last session. So our first speaker is Dr. Borivoje Nikolic, who holds the National Semiconductor Distinguished Professorship in EE and CS at UC Berkeley. He's well known for his work on digital and mixed-signal circuit design, VLSI implementation of communications and signal processing algorithms. And of course, he's a co-author of the classic text, Digital Integrated Circuits and Design Perspective. We're still waiting for the updated third edition of that said text. Bor is an IEEE fellow and has received numerous past paper awards at ICC, VLSI, and SIGARCH. And so today we're excited for Bor to talk a little bit about digital and mixed signal and bring that perspective to the workshop, and more specifically to speak about an increasing trend towards digital and mixed signal generators. So Bor.
Thank you, Chris. Well, thank you for staying here till the bitter end. I've changed this talk about 5 to 6 times this afternoon. It's a privilege of going last as well because a lot of stuff has been said already. So I'll try to keep philosophy part to a minimum here because a lot of that has been already said by Dave, Mark, Serge, and others beforehand. A lot of this work is not mine. It is done by a lot of my colleagues and students. Some of them are sitting in the cheap seats in the back. To cut to the chase, computing has gone through these different waves where we, early on, when I was a little kid, computers were used. Just mainframe computers were there to solve large numerical problems and crunch a lot of numbers for scientific computing. That was replaced by a revolution of personal computers that rode the wave of World Wide Web. That was in the 2000s replaced by the smartphones and apps as a driving application for them. And now we are going towards the next wave, and that next wave is not completely clear what is it going to be. There is a wide number of applications that are out there that are driving the computing in the semiconductor industry, that are in healthcare and wellness, medicine, education, autonomous driving, entertainment, and visualization. But even though it looks like machine learning is tying many of those together, machine learning is not the application. It is a technique that is in there. So there is no single driving application, and we need to figure out how to specialize a lot of these computing platforms for their particular applications. But we have seen this slide pretty much in every talk today that the chips are expensive. And I pulled an updated one. This came out last month. Look, the numbers shrunk. But they're still very large. If you're looking at the 16 nanometers, it's a $100 million chip. It really depends what kind of a chip it is. And on the bottom, there is a quote that Brosek has put out that it is 8,000 engineer years if it is a really, really big NVIDIA Xavier chip, or 16 million engineer hours. So why are things expensive? And maybe I can argue with Mark that reuse is one of the big issues. There is a lot of IP out there, but it is typically black box. It's not modifiable, and it is not what differentiates products. The common stuff that we all use is not commoditized, and we always have to pay for it. 90% of chips that you look at now have the same components, and we build them over and over again, and we pay for them over and over again because we don't know how to change them. The approach, Mark, I think, has mentioned that a long time ago, 15 years ago or so, build generators instead of instances and try to use a generator as a way to capture designer's intent. The idea there is to use generators to facilitate this reuse via parameterization and incremental extension of the generator and not the instance, and apply the same thing to verification because verification is as expensive as the design. So what I'm going to go mostly are the examples of how we have done that and what is out there that we have put out in somewhat disorganized fashion, and later I'll come back to try to pull that together and where is that, how is that going to end up being organized. We have digital generators and analog generators. In a digital world, we use Chisel, which is an open source hardware construction language where libraries represent hardware primitives. We use methods to connect those classes together, and then by executing that, the software constructs the data flow graph that maps into the RTL. It compiles it in intermediate form, which is called the peripheral, and then it emits Verilog, C++, and some of the verification collaterals, if people are interested. BAG is written on top of Python. Chisel is written on top of Scala. And BAG is also there to capture designers' intent when building analog blocks. One of the important things that generators enable is this Agile Flow, where every time we would like to add a new feature to change the specs or add features, we do that by updating the generator, not the instance. And we go through the entire design cycle of what Dave has described earlier today as tape-ins, where we pretend to tape out, but don't really do it, get very close to that process, but where we exercise the entire design flow and verification as going through that. Everything is based on RISC-V ISA. I don't have to talk too much about that. There are many, what is important about that is this really expensive part of a software that we are trying to reuse, an open source software community that will help build things that are common for everyone. There are many research and commercial cores that are built on top of this ISA. Examples of ones that we have heard about here are Ariane and Pulpino that come from ETH, and Rocket that comes from Berkeley. Let's take a look a little bit about how we conceptually use this to build differentiated systems. So the first thing here that we can look at, there is a RISC-V Rocket chip generator. It is a parameterizable SOC generator written in Chisel. It has a lot of stuff. It includes the Rocket core by default. It's an in-order 5-stage core. Has a standard slot for a coprocessor that is named ROC, and its own native bus, which is TileLink. And then you can connect, there are ports for connecting peripherals. And comes with a few standard peripherals, comes with L1 cache, and you can add memory to it. It was developed in Berkeley, but it is moving. Mostly it's maintained by people outside of Berkeley, and it will be a part of CHIPS Alliance. You can parameterize this by changing generator parameters. You can do that if you just look at config.scala. You can change the parameters there and change a few things. Exciting thing that happened yesterday, look at this. Instead of a scratch pad, it got L2 cache, publicly released yesterday by Sci5, that can be used for building cache-coherent multi-core systems. So you can change the cache organization, number of cores, and so on, and there are prescribed builds for FPGAs and ASICs. The second option for modifying this is if you like to develop your own circuit for something and validate it, see how does it work improve a real system. For example, you have a memory macro that you claim that will drop the energy of a core. We can develop that and drop it in there and see how it really works. That's what we did a couple of years ago. Or you have even your own technology, and there is a lot of fancy technologies where people try to build machine learning accelerators, and you can drop it in and see what it really does to the system, if it saves anything. Some of our colleagues have done that. And had for photonics technology, and had a paper in Nature a couple of years ago. You can customize it in a third way by building a differentiated RISC-V core. Here, Rocket chip comes with a standard 5-stage in-order pipeline, but what we might have heard from Brusek that they've modified that and used it any way they like. Berkeley has been playing with out-of-order cores, open source out-of-order cores, and we have heard there was a paper last year in CARB, and there is a paper this year in yesterday's CARB talking about how you can analyze Spectre-like attacks and immunize your chip to that. As an example of how quickly you can bring this to results, we had a chip last year that basically 2 students built in 4 months through a series of these tape-ins, where they basically took out the in-order core, placed an out-of-order core in there, went from basically a concept, an RTL that was not really performant or synthesizable, to something that could have been built and added some resiliency features to that. It was in last year's VLSI and a couple of issues ago of solid-state circuits letters. Option 4 is to develop an accelerator and attach it as a coprocessor in the ROC slot. A standard thing that comes from Berkeley is this 4-lane vector accelerator that you can have multiple copies of, but in each of those instances of an accelerator, each one of them can run 4 double precision or 8 single precision or 16 half precision floating point instructions that are good for running dense and sparse linear algebra or machine learning workloads. And that was open sourced at last year's RISC-V Summit. The 5th option here to customize an SoC is to add a peripheral device. And this peripheral device would be attached to the back of the tiling crossbar. And that would often be some kind of a DSP device, generally, that would work with the outside world. May have an analog front end and signal processing chain. To implement a signal processing chain, we like playing with chisel. Chisel has some interesting advantages in there that you can build these type agnostic generators, meaning that you can be number representation agnostic, develop a generator in a floating point, and then change, use exact same representation, but just change the type to convert it to a fixed or complex number type. It's a convenient way of verifying a design if you have a floating point golden model. When you develop DSP generator like that, it is really important to have a common wrapper that we would like to put inside a rocket chip and attach it the way we described. BSP Block is a way to do that. And that's just, it's kind of this basic building block of DSP functionality. The standard wrapper attaches streaming interfaces at the ends that could be axis stream or tile link, whatever you like, and then attaches a control port to it that directly maps into a rocket chip, where you can program the control and status registers, like in many other cases people do. And that works really well. Try it out. It is a very quick way of building adding a DSP function to a rocket chip. When we have a description of a design, it is a good idea to try to emulate it first. So Firesim, we have heard quite a few times about Firesim, and SIGARCH has given an update yesterday. It's a way of cycle exactly simulating large SoCs or networks of large SoCs on cloud FPGAs in tens to hundreds of megahertz throughputs at really, really low cost. I mean, there is no cost of ownership. It is just the rent per hour of a large number of FPGAs over there. Typical targets that we have seen those used for is evaluating an architectural feature of interest of a community that would be here, or perhaps validating an application performance on a pre-silicon SoC. We've seen one example yesterday that Alan talked about, running a PageRank on various, I think 12 different instances of rocket chip with vector accelerators, multiple tiles, and so on, and concluding that the best thing is to have more tiles than less and less vector accelerator attached to each one of those. Now, when we have that digital part of an SoC, built the thing that, a glowing thing that is missing there and the elephant in the room that, nobody really talked about today is the analog stuff. We need to have a way to build differentiated analog blocks without having to pay enormous amounts of money for licenses for something that is out there. We have an analog generator mostly developed by a group of my colleague Elad Alon with contributions of many others. A lot of our students have now bought into analog generators, not building instances, but building analog generators. And it fits into a flow that looks like this. It has 3 basic components. Schematic layout generator, measurement manager, and a design script that are reasonably decoupled from each other. It does not invent circuits. You supply an unsized circuit to it. What it will do, it will generate a layout for it. It will instrument that design to evaluate the performance of it, and then run a design script that will update the sizing and evaluate each of those instances of a design that are being generated along the way to build new optimal design. The way how you can do that, the bottom thing, the main thing, the body of bag is the analog generator. That is a hard and difficult thing that is built in there on top of basically Cadence Virtuoso. But the design script is something that is very interesting. We have started first with something that is an algorithm that is taught in classes for sizing op amps, then moved on to, there are no good known algorithms for every single analog block that is out there, so moved to a tabulated design. It is a table of sizes versus performances of different transistors. But lately we have been experimenting with ML, and ML has been working really well on now, when we have a digitized design, binarized design, you can let ML design things for you, if you can set the constraints right. It is unclear, do you still win overall, because, training takes a while. There is a large number of generators that we have built, starting with a whole bunch of comparators, to switch cap DACs, resistive ladder DACs, to building the entire SAR ADCs. A big move here that you can realize when you have a bag, you can rotate a design. For many people in this community, that does not mean a lot, but if you're an analog designer, you need to rotate a design in a new process. It's really hard. You can rotate it and time interleave it as shown on the bottom, and then we have, high-speed SerDes, complete transceivers, transmit and receive parts. And to show that we actually have a generator, we can design one generator and move it across design. So ADC Core, time interleaved ADC Core that is shown here is shown in ST28FD SOI, Global Foundries, fully pleated SOI as well, and then TSMC 16 nanometer FinFET. You can modify the number of taps in your serial link, or move the entire thing from TSMC to Global Foundries. We went and exercised a lot of, by building this flow, by building a lot of chips. And here is a gallery of a lot of chips. Some of them have not been published, so they're slightly obfuscated in here. But this is a lot of chips and a lot of learnings. None of these chips were perfect. They were great learning opportunities, and we took an advantage of those to update generators. And the list of failures and learning opportunities is long and is the subject of another talk. I'll talk a little bit about things that worked pretty well. So here's one signal analysis SOC in 16 nanometer FFC that is an example of what I was talking about, how you can build an SOC. It's a 5 by 5 millimeter die in TSMC 16 nanometers built a couple of years ago. And what you will find there is a rocket chip with actually 4 vector accelerators in there. And then on the bottom is a custom DSP, custom yet runtime programmable DSP engine that is attached to the bottom of it, that consists of 7 gigasamples per second time interleaved ADC. followed by a DSP chain that has a ADC calibration, tuner, FFT engine, filter, and so on. The results of that went up to the rocket chip, and rocket chip could analyze what signal was acquired over there. The entire design is open source. You can access it on the link that is on the bottom. And it took 14,000 hours between Berkeley students, Northrop Grumman, and Cadence. The chip was fully functional. ADC was evaluated, you can see here, and then you can move a signal, you can observe the signal. Beautiful thing is here, every part of the DSP was mapped onto the rocket chip, so you can acquire these waveforms and look at them and actually stimulate it based on the initial, the way what the design was verified with. And then you can move that and use the DMA engine and the vector accelerator to accelerate, trying to look for the features in there. And the bottom here is showing a radar application showing 4 nanosecond radar pulses that are synthesized but analyzed by the chip. We did another interesting exercise. This was a part of a DARPA project, and like ProSig's team, we were asked to map this to a different process, and can we do it in a relatively short amount of time with less than 20% of effort. So this is showing porting from 16 FFC to 14 LPP from GlobalFoundries in 2,700 hours. Majority of those hours, a huge majority of those hours, went into the back port because the primitives had to be rebuilt for the new process. But we started from scratch, and it is completely reusable. The second largest chunk was the management from our partner companies, and then very small thing went into the digital flow. We use a lot of these similar generators to build another chip in the exact same process, in exact same tape out, in parallel with much less of an effort. And this was a very differentiated chip because it was a sparse signal analysis chip. What it meant there is that it had these subsampling A to Ds. They were running this time at 4 gigasamples per second, not 7 gigasamples per second, because we had a learning opportunity there that reduced the speed, the sampling speed. But then it was followed by these co-prime FFTs, co-prime subsampling factors and different FFTs, and you can reconstruct the signal out of that. This was done in total of 3,000 engineering hours. The same test chip had a SerDes generator in instance, and it is an evolving SerDes generator. It is also available on GitHub over there, and it is a complete transmit and receive chain that operated last year at 15 gigabits per second. It was supposed to be 16, but there was a learning opportunity there too. And it is updated now, and we have newer versions that are running at significantly higher speeds. The last thing that I would like to highlight here is the ADC generator as what is the most complete published generator that we do have so far. So it is a complete generator of time interleaved successive approximation ADCs that scales from a gigasample per second, which would be 1 slice, to something that will comfortably work over 10 gigasamples per second with roughly 6 to 7 bits of resolution, depending on the process. And it is done in one particular layout engine of BAG, which is called Lego, and has all the components. It has a sampling front end. Basically, you go from the pin, it generates the interface from the pin to the sampling, SAR logic, and a retimer. And there is a lot of options there where you can change the clock, pulse width, source, follower, what kind of a sampling would you like to do, and so on. And it is implemented in BAG. And essentially what the BAG does is, runs a specification handler. From there, updates the analog components of each of these blocks, runs the whole thing around, generates the block, adds the chisel backend to it that is needed for finishing the retiming, and wraps it around and drops it into a chip. When you look at it, what we have now, the performance actually surprised me of this. Is what we ended up having is a number that is that results in a figure of merit that was the same as the state of the art. However, when you take a look at these numbers from ISSEC, they did not. Every single one of them had to invent something to get there. There was a circuit innovation. We just used vanilla techniques and ended up optimizing it better to match the performance of the state of the art. By adding, BAG doesn't prevent us of adding new things to it, but I believe in adding one thing, changing one thing at a time here. So what do we have? We really like the generator-based approach, and we do it, we use it in an agile way. There is a lot of reuse that is happening, way more reuse than what we have ever seen. And we are putting stuff out into the ecosystem. There is there is Rocket Chip, there is Chisel Bag, there is Firesim. We are working on a lot of other generators. Many of them have not been published, but they do exist on GitHub, and feel free to access them. We have put reasonably good tutorials how to do things. So there is a Chisel bootcamp here, and a Bag bootcamp, and there is a Firesim, which you will see one of the things that have been mentioned previously. All of this is fairly disorganized, and stay tuned for in the next 6 months or so. Maybe there'll be one-stop shop to get to a lot of Berkeley-generated generators in there. And as I mentioned before, I did almost none of this. Other people did it, so I thank them a lot, and I thank our sponsors, and I think I have a few minutes for questions. That was a part of craft. Yeah, so if you look at the bag, or probably hopefully bag in a couple of months, what there will be 3 layers in there. On the very bottom, there will be a technology plugin. And at the moment when you access bag, you cannot see that because that is protected by the NDA. That is essentially a rendering of a design kit. Design rules are coded up in Python to be accessed by the layout engine. The middle layer are 2 layout engines that exist there, Lego and XBase, that are basically forming a layout, along with the measurement manager, a schematic sizer, and the design script. And on top of those are supposed to be generators. They're accessing these intermediate engines. What has been a challenge, and what we'll try to do, is to, we did not have a clear separation of the generator, circuit generator, from the layout engine. Often, generator ended up being buried inside of a layout engine because, honestly, we did not know what we were doing and how to separate that cleanly. But with learning, this separation is going to become clearer, and it is going to be a lot easier to push things and reuse them in the open source. But yeah, SerDes, in brief, SerDes is different than A to D converter. So the generators that are sitting on top of the layout engines do have to look different. Many components are reused, though.
Quick question, really quickly. So you mentioned a lot about reuse, and I know like Chisel has a lot of, or Rocket Chip has a lot of external from Berkeley reuse. Have you seen kind of external reuse of some of these bag generators, or mostly it's internal reuse so far?
We have seen the companies are using BAG, but unfortunately this happened through clones because of not a very good separation between the first technology, the layout engine, and the generators. So they have cloned the entire things, and then it's really difficult to push back. So that's the one big reason why this needs to be separated.